Hi everyone, how are you? In the last lecture, we started the introduction of reservoir simulation and we covered almost 37 slides of our lecture. Today we will continue where we have stopped in the last lecture. So we were talking about the basic introduction, what is reservoir simulation, like what are the applications, what's the mathematical background, how it is done, and so far and so on. So we said that reservoir simulation is a tool which is combined by physics and geologist and mathematics, computer science, and reservoir engineering. Well, when we gather all this input in a software, then we analyze the data, and then we manage our reservoir based on the data that we have. Now, in order to do the reservoir simulation, what kind of data is needed? This is the question number one. First of all, we need the PVT data, which we call it the reservoir fluids data. Then after that, we need reservoir rock data. And before that, we need a geological model, the model of the real reservoir, which is developed by the geologist and geophysicist. Now, since as I said that we need a lot of things in order to run the reservoir simulation, there are we divide our parameters or data into two main sections. One are the deterministic, which we are sure about them, and some of them are probabilistic, which we are not sure about them. For example, let's look at the general introduction for what is the deterministic data. Well, if you convert from feet to meter, it is deterministic. You are sure about it that it is. If you convert from feet to meter, this is the result we have. But in the probabilistic, we are not sure about it. For example, you have a roll, you want to die it, you don't know whether it will come 3 or 4 or 5 or 6. So you are not sure. But so we have to just do the probability. And probability of cutting 3 in out of 6 is 1 by 6. That's the probability that we have here. So we are not sure, we just do the probability calculation. Like when we go for the real reservoir, we are not sure. For example, the water, saturation of water. Exactly what is the saturation? Are you really sure about it? uh, for example, the saturation of oil. Are you really sure about the saturation of oil? Okay, porosity. Like, are you sure about the porosity of all the reservoir? If you remember, the reservoirs are not 1 feet, 2 feet, 5 feet, or 10 feet. Probably they are in kilometers, maybe 100 kilometers, 50 kilometers, or minimum 1 kilometer. So, are you sure about the properties that we have? So, based on that, when we do this reservoir simulation, we look at it. What are the data which is uh, deterministic, and what is the data which is probability, which we are not sure about it. So all models that we have is a combination of deterministic and probability. Both of them we have in this situation. When we run the reservoir simulation, what we do first, we define the grid. As a first in the geological model, we define its structures. As a geologist, we define its stratigraphy. Lithological means what kind of rock it has, and of course the property like petrophysical property like porosity, permeability, and so on. So we need to know the right structure, the right stratigraphy, the layering of the geology of the reservoir, the what kind of minerals it has, what is the modeling it has, and so on. So once we have our reservoir model, actually we divide the reservoir into small grid blocks in order to to make to give it an address to reach the reservoir, the every corner of the reservoir. For example, here in this case, if we look at it, uh, let me show you. If we have the reservoir like this one. Now, if I want to, this is our tank reservoir here we have. Now, if I want to reach at any point, uh, if I want to reach here, or if I reach here, this is all one. So, reaching here, how you can identify, or how you define the property. Maybe porosity at this point is 20%. Porosity here is maybe 25%. Porosity here maybe is another 18%. So how you are going to define it? So what we do in this case, uh, what we do in this case, we have the reservoir like this one, and what we do, divide this reservoir into these small sections. We do the gridding of them, as I said before. We do the small gridding of them. We make them in a small blocks. Here you can see. Here you can see that we do it in a small blocks, and we divide like this to them. Now, what is the benefit of this gridding? This I will explain to you right now. Let me just make it. Well, they are all equally divided, and they are not separate. Usually we divide them equally. Okay, now I made the grid block. Now, for example, in porosity here, each of them has address. For example, this block, address of this block is 1 1. This block is 1 2, 1 3, 1 4, 1 5, 1 6, 1 7. This is 2 1, 2 2, 2 3, 2 4, 2 5. So if I write the exactly here, what is the here? Here we have 1 2 3 4 5. So this is 1 space 5. This is the address of this one. For example, if we have you want to do equip the address of this one. So here, for example, here its address is not 1 5. Let's say it's 2 1 2 3 4 5 6 7 2 7. So now once we have the address, we can set up the properties. For example, porosity, permeability, whatever properties we have here, we can set it here. Whatever properties we have here, we can set it here. So that's the reason that we define into the grid blocks. And then, as I said, we divide them into three grid blocks: 1 2 3 4 5 6 7. Well, this is a very simple model we use just for the explanation purpose. And but actually in the real model we have thousands of cells and sometimes millions, and the process of converting this section, this big reservoir, into these small grid blocks, we call it a discretization. Now this discretization process, which is defined as to convert the big reservoir into small pieces or small grid blocks, is actually based on two different. There are two kinds of discretizations. One is the space discretization, volume discretization, as you see here, block to block. Other one is the time discretization. For example, today the oil production here from this in this block, the oil saturation, let's say, is 80%. But maybe after 1 year, oil saturation here is 70%. So time is matters here, because with time the saturation is changing in this regard. Further we go ahead, we define, when we go for the geological model, we have to define the topography of it. And topography means like layering, like how thick is the reservoir, what is the pay zone thickness overall, and so on and so on. And later on we have to define the petrophysics properties, and again they are very difficult uh, to find out the properties of all the reservoir. For example, we can find the permeability near wellbore, we can know that, but we just use the average or some methods to find the permeability and porosity and water saturation. So what we do, we use the geostatistical modeling in this case, and geostatistical modeling in order to define the properties here. Now we have two kinds of model. One is the static model and another is the dynamic model. So once we develop the static model, means we whatever data we have, we put it. We just put it into it. For example, we have well and seismic data. We develop the strategic model, structural model, stratigraphy model. We put the reservoir grids. We put all the data into it, and so on. But it has to be validated with production data and well test data. It means that, for example, we made a reservoir model on the computer and a software, but it is producing 10 barrels per day, while the real production is 1000 barrels per day of the well. So no, this model, you cannot use this model for forecasting or prediction or developing your plans for this reservoir. The real your model that you develop in the software has to be same, give the same production rates as given in the real data, as from the real production well. So both has to be matched. This called the dynamic model. What we do, we update the parameter, we check where is the problem, why our model is not giving the real results as given by the real fields, and so on. So in the process of making reservoir simulators, three equations are three basic laws are used: conservation of mass, conservation of momentum, and conservation of energy. And as we go ahead, conservation of mass, the defined definition, how we define it. We say that whatever mass is entering inside this container or this storage, whatever it is going from here, whatever is coming out, remain is inside. It's like a bank account. For example, in your bank, you have $100 and you enter $20 more, okay, and then withdraw $30. So if you initially there were $100, then you added $20 more, so now it becomes 120, and then you withdraw $50 out of it. So now the storage is $70 because 50 is withdrawn. So using this simple mass conservation principle, we have developed big simulators. I mean, the idea looks very simple here, but when we apply it in the oil and gas industry in reservoir simulation, it actually reaches to the big, good and positive effect on the industry and reservoir simulation and so on. Let's move ahead. And as I said, we have three basic: conservation of mass, momentum, and energy. For the momentum means something which moves. And here in oil reservoir engineering, usually we talk about the Darcy's equation. So, as I said, the as per ideal condition, we are considering in this course single phase, only one dimension, and horizontal flow. Means we are not, as you know, the reservoir may have maybe two phase or three phase. Maybe the flow is flowing in one direction, two direction, or maybe in radial direction. So flow may be horizontal, vertical, or lateral, or so on. So there are so many scenarios and complicated things come up. But in order just to develop the concept, we just talk about the single phase and so on. Here are some equations that are developed using conservation of mass, energy, and here you can see here. And this we are going to talk about how these equations are developed in the upcoming lecture. Today, just to give you an flavor that okay, this equation uses as a foundation are used as a foundation for reservoir simulators, saturation and pressure, especially mainly saturation and pressure and so on. These equations are solved using the mathematical techniques, numerical methods, especially finite difference, finite volume. There are so many methods available to to solve them. Okay, then after we develop these models, we upscale them. Upscale them means uh, we look at the properties and we look at the heterogeneity. Like we have the fine model, we have the, for example, our main objective that our model has to behave as the real reservoir model. So in that case, sometimes we upscale them. For example, here you can see the blocks are small, then we make them bigger codes, bigger uh, grid blocks. If you run the simulation for this one, and if you run the simulation for this one, they are different. It will take double time than this one because here the blocks are less, here the blocks are more. So we don't want to put so many grid blocks so that our simulation takes 7 days, 10 days, or 20 days. Or at the same time, we don't want to make it so simple that it gives us a very error. So we call it upscaling. We have to upscale each cell and we look at it how it all goes. Then we have the properties, permeability and porosity, how we define them. We have three ways to define them: arithmetic average, geometric average, and harmonic average. Uh, I'm sure that you studied them in reservoir, rock course, and so on. Definitely, we have to define the permeability, effective and relative permeability in the reservoir simulation that you will see, and so on. The main one of the important parameter that is going to be used in reservoir simulation is the transmissibility. For example, now you have a, a reservoir which is divided into the grid blocks as we discussed. Uh, Here you have the reservoir which is, so how the fluid from this point from this point from this point goes to this point. How it is moving in this one from here to 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 here, or to here or to here or to here. So we have to define all of it, that how it is all uh, behaving. So in order to define it, we convert them, we call them uh, the transmissibility function. That transmissibility is the one which tells us that how we are going to define this section. So for example, here you can see, and what we have to define, we have to define the saturation, we have to define the flow rates, the permeability and pressure and so on. So we have to know how easily fluids can flow between them, and expression is I plus 1 usually that we use in the one. Now further going ahead, we have, when we go for the reservoir simulators, we have two kinds of reservoir simulation models. One is the black oil, here you can see the black oil, and the other one is the compositional model. We have two models here that we are using in reservoir simulation. In black oil model, we are just using the phases like oil, gas, and water. Here you can see labels are gas, oil, and water. So we have gas, we have oil, we have water, and rock. These are the components. This is how we define our model in reservoir simulation. But in the compositional model, we define complete composition. For example, we have ethane, methane, propane, butane, so on. We don't define there's oil. Okay, there's oil, but what components of oil? Like pentane, hexane, hectane, octane, nonane, decane, and so on. So we define all the processes in the in this one. Well, in some cases, now the question comes: which one is more accurate? Well, both cases can be used in particular case. Okay, there are many studies. In some cases, the this simple black oil model may work, but in some cases, the compositional model is important. For example, when we talk about the water coning issue, the issue of water raising towards the completions, maybe we have to use the compositional model. Then, if you are using, let's say, injecting the polymers or EUR processes, so you have to use the composition. But once you have the very simple process, like you are just injecting the gas and you are just, so you can talk about the simple black oil model. So both can work, but we have to make sure that which one is more perfect and so on. So when we talk about the reservoir model, what we do? Well, we input, gather all our data. Now, for example, you are working as a reservoir simulation engineer. The company has hired you. So what you will do? What will be your assignment? What you will do? You will, first thing, you will gather all the input data. You will record fluids, rock data. You will have fluid data. You will have pressure, well test data. You will have PLT, production logging data. You will have completion data. You will have data from the geology department, production department, drilling department, logging department, well test data. You will have from PVT data. You will have rock data. So there will be a database where all this data is stored, and you will have access of it. Then after you have data, you are going to define your grid block size. What kind of simulation you are going to do, and so on. And then you will define the wells and pressures and so on. So you define your data, you define the grid blocks, you define the control, how many wells you are going to put, and after you set up your, you can run the prediction, and I will show you how it is done. Well, as I said, once you run your simulation, okay, you get your results, but you have to make sure that the production rates has to be matched with the real performance. This is the first thing. I mean, you cannot look into after 10 years. For example, now your well is producing, in 1 year it has produced 50,000 barrels. So this is the real performance. So your model that you have developed and run on reservoir simulation, it has to show that the reservoir fluid you have produced is 50,000 barrels in a year. If your reservoir model says 100,000 barrels per day, it is not going to work. So you have to adjust the parameters in order to correct this errors and make sure that the simulated and the real both gives the same results. We correct adjust many parameters here, and here you can see the chart. We have the gas oil ratio versus time. The one is the simulated, and this dotted one is the real one, and you see now they are in quite good alignment in this case. Here here you can see that. So the real data, this is the observed data and predicted data. Both has to match. Once it is matched, then your model is ready for the prediction. And it is not an easy job to history match the one. Well, there is all in reservoir simulation. There is always an uncertainty. As I said that the one of some of the Belgian Kurdistan region, they were not expecting the water production. It was, but after a few years they started getting water in the wells. Well, there is uncertainty always. So in reservoir simulation, always remember that if a man will begin with certainty, he shall end up in doubts. But if he will be content to begin with doubt, he shall end up in uncertainties. Well, what are the problems, uncertainties that can happen? For example, the size of reservoir. For example, you expected the size of your reservoir is 1 kilometer, but actually it is 2 kilometer. And how much is the aerial extent? What is the thickness? So you have to make sure that you are not uncertain. You are sure about the size of the reservoir. Of course, bigger size means more oil and different scenario. So size, contained, and net to gross thickness, and all those things matter in reservoir. Well, you have to make sure that there are what kind of faults it has, folds it has, any fractures, and so on. Make sure the rock property, permeability, and porosities are fine. They are not wrong. And there are many fluid properties like formation, volume factor, viscosity. You have to make sure that your laboratory gives you the accurate results. Or sometimes even you don't, some of the data is not existing in your laboratories. For example, you don't have the bubble point pressure, which is the most important parameter in the handling of reservoir simulation. So reservoir simulation model, as I said, there are two models in conclusion. One is the black coil model, other one is uh, the composition model. In this course, we will run both the models. We will show you both the models, how they are run, and what are their benefits. We will have lots of case studies using those models and so on. Well, reservoir, there are so many applications that we do. Well, in the early stages, we look for the development plan. For example, now, how many wells we need to put. For example, we have the reservoir here also in circular. Okay, how many wells we should put? Three, four, five, six. So after we have the history matched reservoir model simulation, we we can put 10 wells and see the production into it. How much oil we can produce. We can put 20 wells. So we can actually simulate the behavior after we have the established successful reservoir model. Then after that, the once you know that this much oil you are going to produce, you can really develop the facility, like what kind of size separator size you need, what kind of, if you are dealing with offshore, what kind of platform you need to install. And in offshore we are more careful because the investment there is more, and so on, and number, location, and types of wells, and which kind of, how many wells you are going to drill, and so on. Then this simulation may be applied in later stage also. And in this case, sometimes when the pressure has declined, then we have to do the secondary recovery or EOR. So we look at the scenarios, we try to do the simulation on the real model, and then we look at the possible and evaluate the different development plans for in this case. Sometimes, as I said, there is a water production problem. There are some gas oil ratio is increasing, and the some of the wells are not producing as per their performance. So you do the simulation, you try to figure out that what's the problem is possible in this matter. Make sure that whatever model you run, it has to be history matched. And as I said, what is history matching? You have to match, compare your data simulated results with the real field results. If both are in good harmony, if both are showing the similar results, then you can predict the performance using your reservoir simulation model. Otherwise, it garbage in will just produce garbage out. Your data has to be good quality, run in a good quality manner. You have to upscale it. You have to make sure that your reservoir model is history match. Only then you can and run the reservoir simulation. Well, this was just the introduction, and thank you very much. If you have any questions, you can leave in my email address, or we can discuss live uh, in the class, online class that we are going to do soon. Now, after this one, we will go for lecture number 2, which is mostly will deal with the Python. So, thank you very much.